Well, hi, good morning. Thank you for joining me in my shop. Today is the 6th of December, 2023. And I think this is day 3 with this radio. Day 2, anyway. So, I've tested the tubes. Tubes seem okay. I've changed one capacitor. Here it is. It looks good. And it tested pretty good. And after replacing it with a new capacitor, the behavior of the radio, the low output, stayed low. Might have been improved slightly. There's also what I would call an open circuit hum, or a high impedance hum. I'm not sure what to call it. A buzzy hum that's quite apparent in the speaker, with the volume even turned up a little bit. So those are the apparent problems. It does receive. You force a strong enough signal into it, it does come out the speaker. So considering the condition of the first capacitor and the test results and whatnot, I think probably the rest of these capacitors are probably in okay shape. Not like new, but probably okay, probably not responsible for the weak operation of the radio. So what else could it be? Well, it could easily be a resistor that's gone high, maybe causing a voltage to go low. So I think since the schematic I'm going to show you in a minute contains some really good information, and we'll avail ourselves of that information. Do some tests on the radio. Could be resistance tests. Could be, a resistance test might be a good way to start, because you don't even have to have the radio switched on to do it. Let's take a look at the chart, and we'll think about what to do next. So this is the schematic here, whoops, and here's the charts I'm talking about down here. So one is a voltage reading chart, and the other one is a resistance reading chart. This resistance readings are done on the pins of the tubes. This is a really useful chart. So is this one. Maybe, I think, just in thinking about it a little more, I think it makes sense to start with this one. The radio switched off. Now there's got to be some other things that are, conditions the radio's put in. Switch on, stuff like that. Cooperation of the manufacturer. This receiver makes it possible to bring you this service. Resistance readings in the B+ circuits may vary widely according to the condition of the filter capacitors. Well, I've replaced the filter capacitor, so their condition is perfect. The gain, the stage gain measurement values above are approximate. Well, the stage gain measurement values are up here. And these, I've never really tried to utilize this stuff. Interesting, and most of the gain is happening right here in this tube. Showing some gain just in the transformer here. I find those values not very helpful, so we're not going to pay too much attention to that. Oh, here we are. Here's a list of things. DC voltage measurements are at 20,000 ohms per volt. That's a good voltmeter. So my vacuum tube voltmeters would be fine for this. AC voltage is measured with 1,000 ohms per volt. It's also quite typical of an AC meter. Socket connections are shown as bottom views. Okay, so these these have the true pin numbers. Socket. So this is shown the way you see it when you look in the radio. Well, that's helpful. They've also put the not just the pin number, but they've put the what kind of element it is inside the tube. That's very good. Nominal tolerance on component values makes it possible a variation of 10%. Yeah, I make it possible for there to be a variation of 20%. Just me. Volume control at maximum. No signal applied for voltage measurements. It's probably not very critical. Okay, well, here's the table. I think we should check the voltages on the tubes based on this chart before doing anything more. Great. Okay, I think I'm ready to start. So I've got the negative lead of the ohm meter clipped to the negative terminal of the filter capacitors, and that's to get to the B minus line, or the common line, I think they're calling it. That's where the measurements are made. First one is interesting. Pin 1 on all the tubes have the same value, 340K. Well, we could do that. We can do that. We don't even have to know which tube I'm doing. Start here. Pin 1. So it's supposed to be 340K. Well, that's going to get to 320 anyway, I think. Maybe not. Okay, that's that pin 1. Let's just put a little more light in here. This is pin 1. What happened? Let's go back to the first pin 1. This pin 1. Oh, is it really all 4 of them? I have to look at that chart again. There's no connection to pin 1 here. Pin 1 is completely unconnected. What's going on? What? Well, it shows all 4 tubes, and all of them show that. Ooh-ha. Let's do some more. There's another pin 1 here. Oh, that's the same one. Wait a minute, these pin 1s are not connected. And what about this? And this pin 1 is not connected also? No, this one. This one is connected. What am I seeing there? So the pin 1 on this tube is soldered right to the chassis. Pin 1 is open, and we come over here, pin 1 is soldered right to the chassis. Okay. So despite the incorrect readings in this radio, they have not actually attached anything to pins 1. Pins 1. Let's just look at the schematic here. So, for instance, here's a pin. This is a heater. There's a pin 1 here. That's showing it going to the chassis. Pin 1 to the chassis. Not done in this radio. So pin 1 often just goes to the shield, the metal shield, on a metal type tube. These are glass tubes, so they are not shielded. Okay. Well, it is what it is. I don't think that's a problem we're looking at all. So the 2 tubes that are grounded give the correct reading, and how can they do anything but? It's the reading between it's this resistor I'm reading. That's what I'm reading. Is that really true? Looks like it. Yep. Okay. Well, pin 1 turned out to be interesting, but not. Okay, pin 2. We'll do pin 2 on the 12. We'll do all the pins on the 12 SA7. Where is that tube located? 12 SA7. Which one are you? SQ. This would be the SA7 here, I think. Be that one. Is there any way I can tell? How can I tell? There's going to be no tube layout. Is there a tube layout inside the? Yes, there is. No, there isn't. There's the schematic is in there, but no tube layout. Oh, wait a minute. Here it is on the bottom. Okay, saves me from having to think. So we hold this the way the radio is, all the way around. SA is the tube I thought it was. It's this one. Okay, very good. Here we go. So we know pin 1 is attached to the chassis pin 2. Pin 2. So the pin 2 should read 65 ohms. Here we go. $57 ohms. That's fine. Okay, next pin over, 120K. Next pin. $120K. I'm on the 600K. One, two. So it's definitely 3 here. Open circuit. Okay, am I doing something wrong? Have we fallen off here? We haven't fallen off, no. Well, this is a dramatic. This is the kind of thing that comes from a problem. Now, what's the problem? The problem is I think I'm on the right tube, but I'm not, because I'm that dull. Let's just see if that's some secondary proof. 12SA7. That's certainly pretty strong proof. I'm on the right tube. I'm on the right tube. And I've got 1, 2, 3 pin. That tube was half out of the socket. It's totally open. Okay, pin, well, we're going to stop right here and investigate this. This is 1, 2, 3, pin 3 of the 12SA7. Okay, let's look at it here. Pin 3. Let me shrink this just a bit. Pin 3 of the 12SA7. Pin 3 is here. Plate! It's the plate. This is a bad sign. This is a very, very bad sign. Plate totally open. How does it go totally open? This gets burned out. Doing a little tricky thing here. Okay. This looks bad. I'm right back to the filter capacitor here. No resistor in the way. This could indicate the death knell of this radio already. I could turn the radio on and look for plate voltage here. That might be, well, I think we'll have to do that. For plate voltage and screen voltage on 4. Now, wait a minute now. Number 4 should give us almost the same reading. We better check pin 4. I'm stopping the pin investigation too quick. Pin 3, pin 4, same resistance indicated. Pin 3, pin 4. Okay, pin 3 again. 1, 2, 3, no doubt about it. There's 3. Pin 4. It's also open. I'm going to start the radio up and look for voltage there. Okay. Switch is on. There we go. We're on the dim bulbs. don't care about what the voltage is, just that there is some there. I'll let this warm up a bit. We look for voltage on the filter capacitors. This is the big one here, 120 volts. We're only supplying it with 105 volts, 120 on the. So that's what we should find here. Here we go. There it is. What's with the resistance measurement? Let's carry on with the voltage measurement. Now I've got this thing operating. Voltage measurements. Okay, so to do that we need a little more voltage in the radio. Power supply output voltage. Not like that, we won't. Yeah, we will. 140, that's pretty healthy. Okay, and then down here now we're probably getting 106. Now what does the chart say? 100 volts, so we're good. Pin 2 should be 75 volts AC. I'm not testing that. Pin 5. Well, let's just check 3 and 4 first. There's 4. 5. Minus 5 volts. Minus 8 on there. Okay, that's good. Minus 25 volts on pin 8. What is happening there? You get minus 25 on pin 8. Pin 8. Well, I think that's the AVC voltage they're talking about here. How would you get minus 25 there? Am I reading the chart right? Minus 0.25. I think there's a point there. Slightly negative voltage on pin number 8. Slightly negative voltage. I don't know. Can I get my probe in there? Minus 1. Okay. Next tube over is going to be I can't. 35Z5. Next tube over is a rectifier. Well, I'm not sure what we're going to test on that. No, it's not. Next tube. Yeah, next tube over is, but that's not the next tube we're testing. Next tube we're testing is 12SQ7. Okay. The SQ7 is by itself here. Voltage. I wonder what's making the little scratchy sounds coming out of the speaker periodically. Not much else coming out. 115 volts on the power cord. SQ7. Okay. Pin 2. Pin 2 gives minus 0.7. It's supposed to be minus 0.6. Perfect. Pin 4. Again, these little minus voltages. Pin 4 and pin 5. Pin 4 and pin 5. So 1, 2, 3, 4. Slightly negative, and 5. Also slightly negative. $60 volts DC on pin 6. Am I on pin 6? Pin 7, pin 8, I am. Pin 6. That doesn't seem right. That is 62 volts. Pin 7, eh? It's getting its voltage through this resistor from over here. 6 volts on one side of the resistor, and on the other side 16 when it's supposed to be 62. Wait a minute, my eyes are going all over the place here. It's supposed to be 60. I'm looking at the wrong line. 60 on pin 6. Okay, let's investigate that a little bit. Pin 6. Pin 6 of the 12SQ7. Pin 6 is here. It's the plate. Plate voltage low. There's the resistor. Resistor gone high. High resistor, low plate voltage, low output. That all adds up. Let's take a look at this resistor. 470. Okay, let me shut the power off before I make a big mistake. Okay. Any voltage hanging around here? No. Okay. What are we looking for now? The resistance was how much? 650K on the chart. It's more than 600. 650, yeah. More than 6 million. It's more like open circuit. What was I just doing? I don't know what I was just doing. Doing something dumb there. No, not really. You're right across the resistor now. 660. $660 ohms, 660K, and it's supposed to be 650. Okay. And this is actually a yellow. Yellow, like that's like 47, isn't it? Yellow, purple. Doesn't like making a connection. about that. Getting some curious readings here. Mostly I think it's just bad contact with the voltmeter leads. 660. Yellow, purple, yellow. I don't know how you get yellow, purple, yellow to be 660. And that's what it's supposed to be at the same time. How's that happen? I don't know. But I can't say there's a problem there. So we've got high voltage on the supply side of the resistor, and on the load side, on the tube side, we've got next to nothing left on this capacitor. Oh, she's a warm one. Something strange has happened here in my shop. In the last month, I found 3 warm capacitors. We'll take a look at that with the thermal viewer. Okay, here's my setup. I've got my thermal viewer here. It's looking right at the side of the radio, looking right at this capacitor. In fact, this has a large field of view, so it sees more than you might expect at this distance. It's going to see a little more. I have a camera here looking at it. We're going to look through that camera now. Okay, so I have this already set. I don't know if it's the best settings, but I will indicate them to you here. Let me just grab a pointer. So this setting up here, but it says 30. That means at 30 you'll see this color. See the red there? So this will basically start showing red just below 30. So if you're down at 25 or whatever this might be, 20, I don't know what it is, this must be 15, 20, I don't know how the scale works exactly, but 15 at the bottom here. So at 15 degrees, this is the color you see, this blue. There's nothing 15 degrees in here. And you see a little plus sign here, right in the center. The temperature at that point is shown here, 23 degrees. Meanwhile, the viewer is showing you the highest and the lowest temperature spots. You see that red thing jumping around here? It's moving around at the highest temperature spot. It reports it here, this red. So the maximum temperature in view right now is 25 point whatever. And you can see hopping around showing you what that point is. 25 degrees, so my house is not quite. My house is a little cooler than that. So it's still some residual heat, or the calibration of this unit isn't 100%. My experience with it is, it's really good. This is a really good thermometer as such. You can see also the minimum temperatures being reported, 19 degrees. That's closer to the temperature in here, which I would guess is 20. In fact, don't I have it on a meter here? I don't. Okay, so what I plan to do is switch on the, oh by the way, this E equals 0.85. This is the emissivity setting. Depending upon the material you're looking at the same temperature, the amount of radiation coming from them is different. That's called the emissivity, so you can compensate for the difference by putting a number in here. 0.85 is kind of a typical number. But I think if you're looking at like a shiny piece of metal or something, you'd really have to consider the emissivity problem. But this will be just fine for our purposes. What do I expect is going to happen? I'm going to turn this radio on, and within a moment, a red area is going to show up right in this spot. Now, how do I know this? I don't know this. I'm putting my finger in front of the capacitor. So you can see my finger. It's that blue colored area. So that's where the capacitor is going to show up. Right in here. And then we'll be able to read the temperature of it and watch as the radio slowly destroys itself. Okay, you're all set here. Okay, I'm going to hit it with the full Monty here. Is everything okay? Are we all okay? The volume's turned down just in case something funny happens. Yes. Here we go. Power on. Something else is getting red. What is that? What is that? Okay, so I'm going to use a masking technique where I'm going to put something in front of the heat. This is in front of the camera here. And try to knock it out. Ooh. Well, it would appear that's the capacitor. How'd that happen? Okay, I'm using my finger again. Ooh. Radio, don't scare me like that. I'm not touching anything here. You know what that is? I think that's the capacitor lead on the right side of the capacitor. Let me try and block that. I'm going to give you a longer shot here so you can see what I'm doing. I want to interfere with it with a nice little radio. Sounds like it. You know what? That's probably that capacitor failing. That's probably what we're hearing. Oh, hurry, Jim. Don't fool around. Here we are. This will work. This will work. Okay, so I'm going to block. See the red dot up here? I'm going to move it just a little bit more. Kind of get it in the middle. Okay, now I'm going to try to block out the red dot, which you're having trouble seeing from there. This is the difficulty here. Any smoke coming from that thing yet? How hot is it? Okay, so we can read the top temperature here. Let's read the top temperature and then we'll find out how hot we're getting. Top temperature is not very hot, 36. Almost certainly the red dot is just bopping around inside here and we can't really see it, the red plus. Okay, so that's not scary hot at all. Maybe I was fooled. Was I fooled? Something else is getting hot now. Something more squarish. Everything. So the heat at the bottom of the image is probably from the tubes. And can you see it's fluttering? It's at the bottom. It's fluttering. That's actually hot air moving. So we're starting to see the actual hot airflow. How can I prove it? Well, I don't know if that proved anything. I just tried to blow it all away. Okay, now I'm going to try to do the masking thing again with this. Here we go. This has a big hole in the middle of it. It's not going to work. Jam. Here, wait, this is perfect. Here we go. Something perfect. This. Okay, I'm going to dip this down just in front of that capacitor. Well, the capacitor is not. You know what? That heat is not from the capacitor. That is something heating up the capacitor. What would that be? Let me feel it again. That's my finger. Doesn't feel particularly hot. Well, so maybe all we're seeing is, maybe it's all nothingness here. So the red area over here kind of matches this stuff over here. You can see me dipping in front of it. So those are the terminals on the tube getting hot. It's just conveying heat over to the capacitor, which is over here. Capacitor is not hot, it's cold in fact. In fact, you can start to see the outline of the square capacitor here. Actually colder than some of the stuff in behind it. And meanwhile the heat is just getting bigger. Okay, so I can readjust this now if I'm careful enough to do it. Here are these buttons, Jim. So I've raised the top temperature now another 5 degrees to 35. You can see more pointedly what it is. It's just, I think it's just terminals. Okay, let me, this isn't the best dipping thing. It's metal, for crying out loud. I'm not watching what I'm doing here. Yeah, those are just terminals. Those two spots are terminals. This part of the bottom here is just the tube bases. Well, I was all excited about nothing. Well, that leaves me without an explanation. Or does this capacitor kind of give out after a few minutes? Lots of fun. Lots of fun. You get kind of a different view here. If I block off the tube bases from the camera, you can see I'm putting this cold thing right in front. And again, block the capacitor. block the terminals that are showing. Yeah, there's no doubt. Okay, false alarm. Total false alarm here. Fun though, having fun. That's the key thing here. Turn off my thermal viewer. This thing has come through quite a few times for me. Not this time. Well, I guess it did. It's showing me what the truth is. The truth is it's not that capacitor. Why did it feel so warm? Scare myself. Probably because everything got warmed up here. It's tied right to 2 pins. The heat's going to travel up the wire, get in the capacitor. Well, let's double check that voltage. Am I crazy? So we're reading to, ooh, I left this clip lead just floating around out here without thinking about it. Incidentally, the radio is plugged into an isolation transformer. 600 volts DC. It's supposed to be 60 right here. 20. What's happening at either side of this capacitor? So obviously on this side is the 20, and on this side it's a 0. This side connects to this resistor, and the big 0 there. I'm just looking, and I'm pretty sure I can kind of see ground wires running around in there. I think. Okay. Why are you low, Mr. Voltage? Again, on the input side to that resistor, we got shy of 100. On the output side, what, 20, but I have trouble making contact with it. Do it here. So I was thinking loose cold solder joint, but that's not very likely. So I'm just trying to move the resistor a bit. It's a little dangerous what I'm doing here. No. Well, so a high voltage, a low voltage would be a high current through that resistor, making the resistor drop more voltage than it should because it's carrying more current. Why more current? First I thought, well, it's going through this capacitor, oddly enough. But that doesn't appear to be the case. So it's not the capacitor pulling it down. What could be doing that? Too much current flow. Too much current flow because the bias is off on the tube. But didn't we measure the bias? The 12S, I think we did measure it. So 12SA, I'm looking on that chart now. This would be on pin number 876. This is pin number 6. Pin number 6, 60 volts. Wait a minute. I'm looking at the wrong tube here. Hold on a second. Everybody hold on. I'm confused. I just want to make sure I'm not confused. 12SQ7. Yeah. Okay, and just a momentary unnecessary confusion. 60 volts is what we should find on pin 6. The other one seemed okay. They're all very small, including which one. I'm going to look at the, just bear with me here. I'm looking at the schematic to pick off which is the grid. The grid is pin number 8. That's just, okay, pin number 8. Looking back at the table, pin number 8 on the 12SQ7 should have 0 volts on it. On that, yeah, 12SQ7, 0 volts, okay. 0 volts on pin 8. pin 8 is, this is pin 8. I already checked this, didn't I? Pin 8. That's a pretty hard 0 there. Pin 8 should have 0 volts on it. Just bear with me again. I'm going to look at the schematic. Why should pin 8 have 0 volts on it? Because it ties right to B minus directly. So it can't be anything but. And that also means that's a B minus connection point. The voltage on the resistor here, the supply side, about 100 volts, and that's pin number 87654 of that tube. Pin number 4 of that tube. Pin number 4 looks like it's carrying B plus. That makes sense. And the voltage pin number 4, 100 volts. And I'm reading roughly 100, just a little low supply voltage. But on the other side should be 60. That didn't hum before, did it? What's with the wire here? Let's read that resistor again. I'm going around in circles, but I'm kind of hung up on this. Wait a minute. Make sure there's no voltage left in the radio. That would look like a 0 to me. Something weird about that wire. That's right, 660, Jim. Next scale up. 660. How does a resist? This is weird. How does a resistor with those color bands, yellow, purple, yellow, end up reading 660, the proper resistance? How does that happen? I'm going to get my little cheater card here. Where is it? Where's my cheater card? Oh my gosh, I've lost it. Okay, so for situations like this, I have a little card, you know, one of those wheelie cards. It's wandered off. It must be traveling around my house. Darn it. Okay. Another way would be some other reference. You know, this is stupid. I mean, I know yellow is 4 and purple is 7. I know this. Is there any chance there's a resistor chart in the back of this book? Tube book. Probably not. Well, this is a foolish situation here. This is crazy. I don't know what else to do except I'm going to cut that resistor out of there. 668. Let me just take a look at the schematic again, because I'm thinking this just can't be the case now. So we're looking at, let's say, pin number 8765. Looks like 4, pin 4 on the 12 SQ. Pin 4. meets up a resistor of 4.7 megohms. What? What has happened? Clearly, I need to stop for some coffee here. Coffee's helpful. I have no shortage of 12 SQ7 glass tubes. I got 4 of them here. One of them has a... that's a little odd. How come it's got a... Oh, 12Q7. Right. So we're going to try a different tube and see if we get a different result. I got to test this though. Make sure it's good before I try it. 12SQ7. Okay, I'm going to give this guy a test. We're going to plug it in the radio and see if the problem's resolved. Okay, 12SQ7. Let's double check this first. A little dark here for me, but 13 is the right setting. Signal level 1, 18L, correct. The numbers are 25100, 25100, and 3760, 3760. 37. Interesting thing is, I don't remember setting it this way when I was testing the tubes in the radio. F. Not that that means much, you know, what I remember and don't remember. Well, my wife and I are suffering from the room effect, something terrible. Here. Yeah, I think everybody is. Okay, is this a good tube? First we'll do the short test. Okay, we'll do the test. This test should come up to 760, so it just has to get up above there. She's a winner. Now I'm going to pull the one out of the radio. I'm going to stick it right in the tube tester and test it again. As I get it out of here, just a second here. Here it comes. And did I pull the right tube out? Maybe I didn't. 12SQ7. Very good. Okay. Now this is the one that's in the radio. Tube testers are not miracle workers. They don't necessarily catch every little thing that can happen to a tube. No shorts indicated. Test. Well, it does test right around, well, it's still warming up. So it's getting, this is the throwaway point. That number I gave is the point where if it's any lower than that, throw it out. So it's definitely getting up. I don't think there's going to be any difference, but we must do the experiment here. We must. I don't know what else to do, so you know, my practice is when I don't know what to do, just do something. Do anything. Okay, so this is the alternate tube in there. We want to read a voltage, so I've got this set now, and it's a little dark in here. Okay, are we ready? Let's get these tools out of the way here. Okay, Mr. Confusing Radio. What are you going to do this time? Here we go. Dim bulbs first. All is well. Look at how much it glows really strong here. Okay, operating the same. Ooh. Sometimes a scratchy volume control is indicating that DC is leaking through it. Now I changed the capacitor off the center terminal, so there we go. What is the voltage on the supply side? 93. Let's give it the full Monty here. 106. And on the other side. Anybody get a reading out of that? Oh my gosh. Sorry. Look at that. 106. 15 instead of 20. I gotta put the old tube back in. It's a little hard to get these out. This is the original now. It did test weaker, didn't it? It's a weaker tube, less current through it. Less current means less voltage drop, means higher voltage at the tube. So exactly the opposite to what we're seeing. Okay, power on. You didn't notice the dim bulbs barely came on, and that's because the filter capacitors have held their charge. Okay, I hear the radio. It looks about the same glow here. Supply side. Oh, full. Give it it was 93, and then the full Monty put it up to 106. Okay, and on the ooh, and on the other. What the heck? And there you go. That's how you correct the voltage in a radio, by doing those things. Does that mean this radio is working now? Let's find out. Where's the antenna wire here? We're going to put the antenna on, and I think this is switched off because I was, as usual, doing things in my other room. So I switched the antenna between rooms. That's turned up pretty high. Dirt there? Sometimes those scratchy sounds are from electronic activities happening in the radio, like oscillations and stuff. Doesn't seem like it. Seems like I'm wearing it out here. I have worn out the problem, whatever it was. There'll be dirt in the ground. Turn it right up. I thought I heard something there for a moment. Can you hear them? I'm going to go turn on the antenna, and that should boost this. Once again, I'm going to let the video play because I'll only be gone for 13.9 seconds. .9. Oh, I didn't touch it. Sound a little bit louder. Oh, exciting stuff. Just in time to hear about a guy's prostate. This thing's picking up stations everywhere. Two on top of each other. How can that happen? Okay, I think alignment is the next issue. Let me take this off here. I just feel a little better when I'm disconnected. Why don't we shove 455 through the radio and see what happens? I think that's a good idea. Okay, we'll take it off the antenna. Surprising how well it was receiving, but it was very, very shrill sound. The shrillness could be because, a little tiny speaker, and that's about that. Or the fact that we're picking up, it seemed like as I tuned through the stations, the tuning range was really broad. The bandwidth was really broad. And so, in fact, I've got stations I can pick up. They're on top of each other as I tune through. So it's a very, very wide mouth on this radio. Okay, now I need the signal generator to settle down for me at 455. So you can see my frequency counter's gone a little wonky. Does that from time to time, and then suddenly it'll start working again. Let's see if I can shock it a bit. No. Oh, there we go. Okay. Now we are hooked up. I've left the ground disconnected. I'm just onto the wire. And what we want to do is fire 455 into the radio and see what happens. I get the volumes turned up. That other hum seems to have disappeared. The what I would call the high impedance or open input hum. Interesting. Okay, there we go. 455. Oh, come on, counter. Don't do this now. Okay, so it's telling me to go have a coffee break, so I'm going to do that. Okay, let's continue now. Just smelling the radio a bit. Okay, here we go. 455. That's a mess. I would say it's not supposed to work like that. I detected two peaks. One of them is at, it's a 490, and another one 430. Two local oscillator frequencies, and so the radio is converting, the broadcast band twice, and then as you're sorting through it, you're hearing the station twice in two places. Does that make sense? I think that makes sense. Okay, so clearly this is an alignment issue. Now, looks like the alignment's done from the top, so I'm going to shut this off. Give it just a moment. We're going to flip it over. What, coffee time already? Everybody's telling me to go have coffee. Okay, there's only one transformer. Only one. Turn the power back on. Get her going. So I think from time to time people fiddle with these screws without realizing what they're doing. They have no equipment and they're fiddling around. So I'm going to fiddle around. So this is the 430 frequency we're hearing right now. Let me just tune this radio and just see if something crazy. Oh my gosh. Yeah, ignore what I was saying. Ignore everything. Let's try this again. Try this again. So we just hear one now. So we're going to try to move that down to 455. So I'm going to move it down. I'm going to boost it up. Ooh, that's too much. That's just too much for that poor radio. Volume is up. Yep. Okay. We'll now try to make this guy come louder. Ooh, this is tight. Ooh, sparks are flying. Sparks are flying. Okay, I've got to do this a little bit differently here. Can't be having sparks flying in there. Let me grab a tool from my crazy large collection of tools. Let's try this one. I can still get sparks here. I can still get sparks from this. Okay, there we go. Tightening. Both screws tighten right down. And we're barely getting anywhere. What does that tell you? Oh, don't short it out. Oh, there, you know what? There's a peak right there. Okay, let's go a little further. Tune in. We're at 465 now. That's better. Okay, 457. Boom! Oh, jeez. Okay, here we go. Okay, 455 this time. 455, just doing it by ear. Another one. Ooh, careful, man. Beautiful. 455. Okay. Let's put it back on the antenna now and see what difference we get. Okay. This is 820 from Toronto, or from Hamilton. Excellent. 860. Picking stations up above 860. Volume's good. Okay. We're really good on the lower frequencies.
Right up top.
It's not exactly a high fidelity radio no matter what you do to it, so. Excellent. Now, there's got to be some more alignment stuff. A screw here. This is the oscillator, and this is the antenna. The antenna adjustment is maybe not even there. Let's take a look at the schematic here. We'll see what kind of adjustments there are. Okay, so this and this, these are the tuning capacitors. You can see they're ganged by, indicated by the dotted line, which the draftsman drew on an angle here. Shame on him. Had it crash into here. Shame on you. So, and fairly nicely drafted drawing, except for that. Okay, adjusting. Here's an adjustment. No. Where is there one? So we're coming in through here, the iron core, and I'm looking at each capacitor here. There are none. Oh, there's nothing to adjust. Wait a minute, the local loss. What's that? What's that sound? Uh-oh. Something just gave up the ghost there. Oh. You didn't see it, but you heard it. I didn't see any smoke come up. Look at, oh man. Something fried right up in this radio at that point. Quickly, I got the thermal thing. Quickly, Jim, act quickly now. Not. I can see what it is. I can see it. It's this capacitor right here. I don't think there's any doubt of that. Why would I bother even doing this temperature thing? Because it's fun to do. Quick, man. Just cooling off as fast as can be. What has happened here? Excuse me. The house will be burned down completely by the time the fire truck arrives. Here we go. Okay, so the setting, I gotta change the setting. Up. Now, it's hard for this to show up in the camera. Unfortunately, it's really difficult. So you have to just bear with me. There's no question that there's a hot banana in there. This is strange to me. I've been doing this for all my life, really. Doing it intensely, like repairing radios intensely for the last, I would say, 12 years. And just in the last couple weeks, I've had a number 2 of frying up capacitors. Can you see how shiny this guy has gotten? And you know what that guy is? What is that guy? I don't know what that guy is. He's not what I thought it was. I was going to say that's the one that goes to the chassis, but that's this one. And just when the radio was working really well. So I'm going to leave it at that, because this will be a bit of a hunt down. Probably the fault is the capacitor itself and nothing more. And wow. I'm carefully viewing this one. Meanwhile, this one is frying up over here. You know what I didn't do? I didn't do with the viewer. I didn't just, pass the viewer over all the parts. I should have done that. I could have spotted that capacitor. A few times I've done the sniff test and been kind of curious about what's going on. There we go. Anyway, okay. Well, that's not bad. Yeah, it's fun. Nobody gets hurt. The house doesn't burn down. And I'm not terribly embarrassed. So that's all good. That's all good. Thumbs up on that. Thanks a lot for watching. And tomorrow we'll carry on with the fried up capacitor problem. See ya.